Chapter 9 is about the periodic properties of elements and the different trends associated with them. So, uh, so what? Why do we care? Well, the potential across nerves, so like neurons, nerves, deals with the motion of sodium and potassium ions. So sodium ions go out and potassium ions go in, and that creates the small potential that goes when neurons fire. And ion channels can differentiate between the sodium and potassium ions because of their difference in size. So there is a trend, actually, as you move down the periodic table, that at least within a column, the size gets bigger, and that's an example of something called a periodic property. So we can predict properties, both chemical and physical, based off of elements' positions on the periodic table. First person to have done this is Mendeleev, and a Russian scientist, as a matter of fact, and he ordered the elements and saw some patterns, and he even was able to predict some of the patterns for unknown elements at the time. And uh, and then when because where he saw gaps, he put the elements somewhere else, and so on. For instance, he predicted gallium and germanium, and he thought they were kind of like aluminum and silicon, for instance, and he was able to predict some of their properties. And so Mendeleev saw this, and he noticed that there was a pattern, but he couldn't explain why this pattern exists. And the reason why is now we know because of the quantum mechanical model of the atom. At least that's a better explanation for what's going on. And specifically, it has to deal with electron configuration. So chemistry, study of matter and its changes, and a large thing that deals with the properties of atoms and molecules deals with the electronic properties of them, specifically how the electrons interact. And that's a big thing. And in the previous chapter, we learned about the quantum mechanical model of the atom. And now we're going to go on and we're going to apply that, and the so what with that is the periodic table and how we can predict certain things, certain properties. And electrons occupy orbitals, and we learn the different types of orbitals via the using quantum mechanical model. But then, we also mentioned for hydrogen, especially, and hydrogen has one electron. So what about multiple electronic systems? And before that, we mentioned this last chapter, but the electronic spin. What is the spin? The spin is the projection of the magnetic field of a particle in any given direction. So the magnetic field goes in many different directions, and overall, it tends to point in a specific direction, and we call that the spin. And if the spin is a ratio of two integers, that's not an integer itself, then we call that type of particle a fermion. And so protons, neutrons, and electrons, these are all fermions. If the spin is an integer spin, we call that a boson. And so photons, for instance, are bosons, and certain nuclei are bosons as well. So you can add two neutrons together, both with a spin one half, they can form a boson from that, or they could. We haven't necessarily seen that. We've seen bosons for something like a deuterium nucleus, where it's a proton and a neutron, and that forms a boson. So, but you can join fermions together to form bosons. But that's a bit more advanced for this class. But I wanted to let you know where this is going, and I hope to inspire you to keep on studying. This is just an introductory class. But the spin, this projection of the magnetic field, and there's an old experiment where electrons were shot and put into a magnetic field, and half went north and half went south, and that's where the spin up and spin down came from. So it's from this experiment. So that's the origin of this. And so it's a fundamental property. As I mentioned, this is for all fermions, and it's this is not it's not part of the quantum mechanical model per se. It's just and also we characterize matter as having, we call it right-handed spin. I mean, we just pick the coordinate system. If you learn more of mathematics, you can learn about a right-handed versus left-handed coordinate system, and the math that we use to model the fermions and other particle bosons. We just give them the right-handed coordinate system. Antimatter turns out to have left-handed, so it's the opposite-handedness of spin. So antimatter is the same as matter, except it's opposite-handedness of spin and opposite charge. So, but it's not included in the Schrodinger wave equation. So we don't necessarily see the spin. The spin matters, but it matters by the Pauli exclusion principle. And here with the orbital diagrams, so we just have the plus 1/2, minus 1/2, and we just use as an arrow. So by the Pauli exclusion principle, you have to have opposite spins. So now orbital diagrams here, for instance, you have the hydrogen 1s electron. So this is just the same as the previous chapter, talking about the quantum mechanical model. The n, the principal quantum number, is 1. The L, the angular momentum quantum number, is 0, giving it an s orbital. The m sub L, the magnetic moment, is going to be 0. And now we have the spin 1 plus 1/2. Of course, if there's one electron, it doesn't really matter if it's plus 1/2 or minus 1/2. But I mean, we think positive. We're very positive thinkers as scientists, so we give it a positive number. Now, Pauli exclusion principle, and this doesn't just equate to electrons. So Pauli exclusion principle, it's for all fermions, using a branch of mathematics called Fermi-Dirac statistics. So if you want to look up that. But the idea is, in the same atom, no two set of electrons can have the same, or only one electron can have the same set of quantum numbers. And so that means for a single orbital, the maximum occupancy is 2, one being plus 1/2 and one being minus 1/2. And this is a very important property. This is the reason why matter has structure. And it's also the reason why energy does not have structure. So matter has structure. And we can tell that because you can't force your two hands together. If your hands were made of energy, so light is energy, light just passes through each other. So light has no structure. Maybe photons themselves have structure, but you can't make something out of energy. It has no structure to it. But matter on the other hand has structure. And that's a so what with the Pauli exclusion principle. This is what gives matter its structure. But let's apply it. So s orbitals, there's only one orbital, so it can hold 2 electrons. P, there's 3 orbitals, so it can hold 6 electrons. D orbitals have 5 orbitals, and these are all from the m sub L's, right? So S has the m sub L 0, P has m sub L minus 1, 0, 1, so 3 orbitals hold 6. D, minus 2, minus 1, 0, 1, 2, m sub L, 5 orbitals, each holding 2, 10 electrons, and same thing with F. Minus 3, minus 2, minus 1, 0, 1, 2, 3, holds 14. And let's look at helium. Helium has 2 electrons, and one's going to be spin up and one's going to be spin down. So they're going to be in the s orbital, and so same things. N equals 1, principal quantum number is 1, L is 0, indicating S, m sub L is 0. One's going to be spin 1/2, positive 1/2, the other one's going to be negative 1/2, and they have opposite spins. And also, which means the electron in there, so you're saying, are they in the same place at the same time? Yes, they are. The 2 electrons are going to occupy the same space at the same time. But the difference is, at any given moment, the overall orientation of the electron's magnetic field is perfectly opposite the other electron's magnetic field. So that's indicated by the spin. And here is another diagram showing that, what I just mentioned. So with multi-electron atoms, if we have orbitals with the same energy levels, we call that degenerate. It's almost like an insult. These are degenerate energy levels. Well, degenerate could be an amazing compliment. Like, you students are all extremely polite and very well driven. You're just degenerate. You're all the same. So that could be a wonderful compliment. Of course, colloquially, it has a negative connotation. But I'm gonna, just like a lone spin, I'm gonna go positive on that. You guys are amazing degenerate students. So, but of course you're not. You have your own individual needs and strength. But we'll get back to chemistry for now. So if you pardon the compliments. So for many multi-electron atoms, the electron energy split, and there's a couple reasons for this. One of the main reasons, not necessarily in the book, is something called the Zeeman effect, but we can talk about that in a little bit. And the lower the value of the L quantum number, the less energy the sublevel has. And this is also another effect of what's called the Zeeman effect. It's not necessarily in quantum mechanics itself. It's due to the electrons. And moving on, let me talk about physics real fast. Something called Coulomb's law. The energy is a constant. I'm sorry, the electronic field, not the energy. See, I'm sorry, the electronic field, and there should be a vector on the E. The electronic field is a constant, 1 over 4 pi epsilon naught, pi being the famous pi irrational number, 3.1415926, so on. E0, that's or epsilon naught, that's the permittivity of free space. And Q1, Q2, that's the charge of 1 over charge of times the charge of 2. So that's charge of 1 times the charge of 2. And then R is the distance between the charges 1 and 2. The force, so if it's Coulomb's law is the force, it's over R squared. So this is the electronic field, and it's the potential energy. So for opposite charges, the potential energy is negative, and it becomes more negative the closer the particles get because they repel. Or I'm sorry, the opposite charge. I'm sorry, they attract. Opposite. I'm sorry about that. The opposite charge is the electronic field is negative. That makes sense because Q1, Q2, one of those is negative. And the strength of interaction increases as the size of the charge increases, and that's just the magnitude of Q1 or Q2. So shielding and effective nuclear charge. So for atoms, though, there are many different layers. So hydrogen and helium just have core electrons, but beyond hydrogen and helium, there's going to be core and what we call valence electrons. So the core are the inside electrons, valence are the outside electrons. And what happens is the core electrons tend to shield. So they shield the nucleus, the positive charge of the nucleus, from the outside electrons. So the idea with that is, so look at something like lithium. Lithium has 3 electrons. It has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. I know I'm jumping ahead, but those 2 electrons in the 1s orbital seem to shield the last electron, and because of that last electron only sees a positive charge of about +1 from the lithium nucleus, and that is known as the effective nuclear charge that happens. Penetration is for, if you remember from a previous chapter talking about quantum mechanical model, we talked about how there's some electron density. So electrons occupy an orbital, and they occupy a space, and some of the space that they occupy for the s and the p orbitals, it penetrates down into closer. I mean, there's between the nodes, there's the electron density closer to the nucleus, and that phenomenon is called penetration. And the more penetration, the effective nuclear charge of the nucleus is going to be slightly higher for a higher degree of penetration. And mentioned here shielding and penetration. This is a lithium atom, and this outside electron only really feels the full. It only feels about a +1 charge, but an electron that penetrates, or at least the density of the electron. Electrons, I know they're like dots, but they're in this picture, but they're really kind of a cloud, a fuzzy cloud that has a electronic and magnetic field associated with it. And in this case, the penetration, the electron density in that area feels a much stronger charge. And here's the wave function. Look at this image here. You have the total radial probability on the y-axis, and then the distance from the nucleus on the x-axis. And you can see here, well, the 1s electron just has no nodes, but the 2s orbital has some penetration associated with it. It has that electron density that's before the node. And that means that the 2s electrons feel less shielding from the 1s orbital versus the 2p. And the effect of this, it changes the orbital energy levels. And then the separations become different. And then this affects how the electrons will add to an atom. And that's something called the Aufbau, or the building up principle, which we'll come to soon. So here, look at this image. This here shows the energy on the y-axis, and the x-axis it's just unimportant. The important thing here is the energy, and that this is potential energy. So remember, electrons have negative potential energy, and that 1s electron has the most negative, the least amount of potential energy. And then electrons will order by lowest energy first. So the first orbital to fill is the 1s electron, and then it'll slowly fill the higher ones. So the textbook says that this is from the effects of shielding. The real reason for this is something called the Zeeman effect. Zeeman, Zeeman. It has to do with, for multi-electron atoms, it's the magnetic field of the electrons causes the splitting on orbitals. So that's the primary reason. Shielding and penetration is important, but it's more the magnetic field interactions. And so the Zeeman effect deals with magnetic fields. There's another effect called the Stark effect, just like Iron Man with Tony Stark. The Stark effect deals with the splitting of electron energy levels from an electronic field, and that's important for bonding and for bonding. The Stark effect is big and comes into play. But that's again for future classes. So the electron orbitals, they fill with the lowest energy to the highest, and that's known as the Aufbau principle. That's just German. It means building up. So builds up and starts with the lowest amount of energy. And then the electrons fill, spin up, spin down. Now, when there's degenerate orbitals or even nearly degenerate orbitals, it depends on the energy splitting, the electrons will fill with something called Hund's rule. They have parallel spins. So when they fill up with the spins aligning with each other. And wrong way. So in electron configuration, when you fill these up, you have the superscript tells you how many electrons are in each of the different subshells. And there's a shortcut to this. You can put the electronic configuration of a noble gas in brackets. So you can only do that with a noble gas. You can't do it with a random element that's not a noble gas. So it can only be for noble gas. And for instance, for rubidium, for writing the 37 electrons, you can skip everything except for the 5s and say, you know what, it's just like krypton, except it's got an extra 5s electron that krypton doesn't have. So that's a shorthand way of doing that. And why the noble gases? Because things tend to bond towards noble gases, so that the noble gases are convenient for that. So here are the electronic configurations, and you can see here, so lithium has 3 electrons, and so is a single electron in the 2s. Beryllium has an extra electron, so spin down. Boron goes up to the 2p, and carbon, now this is Hund's rule. So we have this extra electron, we can either put it spin down, or we can put it spin down in a new orbital. It turns out it has a parallel spin to the first electron in its new orbital. And Hund's rule has been called the bus seat rule. It's also been called the swimming pool lane rule. I like the swimming lane rule because I like to swim, and it's really nice when you get your own lane. But if you don't have your own lane, then you're sharing your lane with someone else, and then you kind of, if you're sharing the lane, the two of you, you each get half the side, and then you swim past each other every lap, right? So but it's better. I mean, it's I can swim with someone in the lane, but I really like it when I have my own lane. So if someone's swimming in the pool, it's an empty pool, and someone's in except for one lane's filled, I don't get in the lane with that person and share the lane. I get in my own lane because I like it that way, right? Because I like having more space. So that's probably the best analogy, if you will. So let's look at this. What are the 4 quantum numbers for each of the 2 electrons in the 4s orbital? So the 4 is a principal quantum number, n equals 4. So C is out because n is not 3. So if it's S, that means L is 0. That's right. And then for M sub L, it has to be 0. So A, B, and D are still good. And then we have, there's 2 electrons. So that means one needs to be plus 1/2 and one needs to be minus 1/2. And so A has them both plus 1/2, D has them both minus 1/2, and B has 1 plus 1/2, 1 minus 1/2. So the Pauli exclusion principle says that you can't have the same set of quantum numbers, so it has to be B is the answer there. So I mentioned before, electrons on the outside, these are known as valence electrons. Electrons on the inside, these are known as core electrons. And atoms are very superficial. They really only care about what's on the surface. So when it comes to bonding, the outer electrons are the ones that interact. So the valence electrons are very, very important for properties. Core electrons are important. It's part of the atomic structure. But the core electrons don't interact with the other atoms and molecules as much. So here show the valence electrons for the first 3 periods. So a period is a row. So the first 3 periods here. And notice that for the 1A, they all have 1 electron. For 2A, there's 2 valence electrons. 3A is 3, and so on. And then up into 8A, noble gases all have 8 valence electrons. And notice that helium only has 2, so because the rest have 8 though. And the definition of valence is the highest number of number n being the principal quantum number. So that's the highest n. And the main group, so the main group is, these are the main groups. The length of the block is, it says how many electrons each sublevel can hold. So the S block on the left can only hold 2, and the P block on the right can hold 6. And the period number, it's from the n, and it has to deal with the principal energy level of the valence electrons. So moving on though, here is the big periodic table. And in the middle, so we have on the far left, we have the S block, the alkalis and alkaline earths. And then on the right, in pink, you have the P block, where you have the noble boron through the noble gases. That's the P block, holds 6. Now the ones in the middle, so the ones included in yellow between the S and the P, these are the transition metals, also known as the D block, because that's, as these electrons fill, they fill in the d orbitals. And then the lanthanides and actinides, these fill from the f orbitals. And notice also for the lanthanides and actinides, they actually, that jumps in. So if you see lanthanum is element number 57, and then it goes to cerium at number 58. So the periodic table should be pushed out a little further, but we keep it this way because it fits nicely on a sheet of paper. It looks a little prettier because it's closer to the golden ratio. So that's a human sort of thing. We just like things to be in the golden ratio and kind of pretty, if you will. So that's why we put the block on the bottom there and not write out the long-handed periodic table. So without writing electron configuration, determine the number of valence electrons in nitrogen. So nitrogen is 5 over. So if you just count it, it's 5 over, and that means it's going to be 5. So it's what I mean by 5 over. So 1 lithium, 2 beryllium, 3 boron, 4 carbon, 5 nitrogen. And that's where the 5 comes from. So how to write electron configurations using the periodic table. So start with a noble gas, put that in brackets, and then count over for the s block, and include 2 electrons for the s block, and if you are in the d or f block, and indicate those electrons, and then indicate the electrons in the p block if there are p electrons indicated, and list the number of electrons as superscripts. So and here's a picture showing that. So you can use chlorine. Chlorine would be neon's configuration, 3s2, and then not indicated there's no Ds. Then you move over and you have 3p, and then up to 5. And then the total chlorine is going to have 7 valence, 7 outer electrons. There are some irregular ones. Right now, we're not going to cover this too in depth. I just want you to understand that they are there. So, but a couple things. The 4s is lower energy than 3d. So the 4s fills before 3d. Well, many of the irregularities come from, you'll see it in the transition metal. There's some that you're going to see that are not expected. But I do expect you to know that the 4s energy level is lower than the 3d. So the 4s fills first. But when electrons are removed, they're removed from the highest end first. So the 4s electrons are going to be removed before the 3d ones. So, and then here are so the other thing with chemistry, so remember it's a observational science, and we're trying to give you the rules, but it's just, we're trying to make sense of it, but these, we're reporting back what we actually see. So as commonly said before, the theory provides, but the experiment decides. So this is what we actually see experimentally. So there's some irregularities here. So you can look at chromium and molybdenum, so 24 and 42. The D's fill before the S's. But you said, well, you just said that the S orbitals are lower in energy. Yes, but this is an exception to their rule. And you can see for copper and silver, same thing. The full D subshell forms first before the, even though there's the empty there's an empty s orbital, but it fills the d before the s. So there's some expected and what we actually find experimentally. So there are some things that are a little off from what we'd predict. So just so you know that there are there. So, and there are certain chemical and physical properties that follow the electronic configurations. And so, for instance, noble gases tend to be unreactive, and also they're gases by their names at room temperature. Alkali metals, they're very light, they're less dense, and they're very reactive with just one electron coming off. So the quantum mechanical model here, it predicts with these common electronic structures, they're going to be they're going to have certain reoccurring properties. And so that's the power of the periodic law, which was observed, and then the quantum mechanical model, which is a theory that explains why we were seeing these observations. And noble gas configurations, these are extremely non-reactive. So it's really hard to get them to react. Can you get them to react? Yes, you can. Even helium. Helium will react with itself. You rip off an electron, and to helium, you can get it to bond with itself. So that's we're going to talk about that in future chapters. So you can get noble gases to react, but it's relatively hard to do. And the reason why they're non-reactive is because their electronic configurations is very stable. It's really low energy. It doesn't want to react because it's already low energy. So then because that becomes inert. Alkali metals, on the other hand, they have one electron away from being a noble gas. And so because of that, they're very happy to lose that electron. So they're happy to lose that electron and then gain that noble gas low energy configuration. And so these tend to form +1 ions, and like I said, react very violently. Halogens need one more electron, and since they're so close to it, they tend to be very reactive and react with things and to take that electron. And they do tend to share, but the others, they can share with other nonmetals, but we'll learn later on something called electronegativity. The halogens tend to steal more electron density than whatever it is they bond with. So it's not a very good partnership with a halogen. So, and ionic charge, electron configuration, ionic charge. So the alkalis group 1A tend to form +1 ions. Alkyl earths tend to form +2 ions. The halogens tend to form -1, 1 over the oxygen family, oxygen group. They tend to have formed -2 ions. And they do this to be to be the same as a noble gas. So that's how they bond. And showing here the picture there, you can see that there's some predictability in terms of the bonding. And there's also exceptions. So, I mean, boron's not listed. Boron it's a weird element. It has its own. But right now, this is a general trend that atoms follow with their ions and electronic properties. A main group element has an outer electronic configuration of Ns2 and Np4. What is the charge for this ion? What is the likely charge for the ion in this element? So it means it's 2 away. So it's either 6 away from a noble gas the other way, or it's 2 away to a noble gas. So it's going to tend to form either a +6 ion or a -2 ion. And it's really difficult to rip off 6 electrons. It's much easier to add 2. So because of that, it's going to be the -2 ion listed there. So Trentonite atomic radius. So, and this is for the main group elements mostly. They can see the lanthanides and actinides and transition metals. They have some other stuff going on. And so what happens is so look at the atoms. They have an electronic cloud, and the size of this electronic cloud, the electronic cloud actually shrinks as you move to the right. And the reason being is that the nucleus becomes more positive. And so the outer electrons, they are not shielded by each other. So they're feeling more of that positive charge. So moving to the right on the periodic table causes the radius to go down. So moving to the right, the radius goes down in size, and then it gets to a noble gas and jumps back up, and then slowly goes down. And you can see that the transition elements, there's some unique stuff going on there. We'll talk about this in future classes and or chapters of this book. And also going down a group, so looking at the alkali metals, as you move down a column, the ionic radius, or the electronic cloud, the size of the atom, size of the ions of similar charge just increase. So they increase going down. So to the right gets smaller, going down the column gets bigger is a trend. So to the right it goes smaller, and going down the column increases. So the smallest element in its pure form is helium. Helium is the smallest element. And of this chart, the largest element is rubidium. There is francium, but francium is very unstable. It doesn't exist for very long. That's even below rubidium. The radioactive means it's stable. And the effective nuclear charge, we've talked about this before, talking about that with penetration. The shielding blocks away the total positive charge of the nucleus. And the total, the trend for this is the effective charge is the total charge of the nucleus minus the electrons in the lower energy levels, and we don't include in the calculation. In shielding, so for multiple electron systems, so meaning more than one, so two or greater, and these electrons, these are simultaneously attracted to the nucleus because the electrons are negatively charged, the nucleus is positively charged, but they're also repelled by each other. And actually, an electron can be repelled by itself, so it's a tough life for an electron because electron is a area of charge and magnetic and electronic fields. So actually an electron can repel itself. So fun fact there. But it's more than one electron, they really can repel each other. And the so not only the repulsion, but then the outer electrons are repelled by the other ones, and part of this repulsion, they don't feel the full positive effect of the nucleus. And looking at this again, so you have lithium. The effective nuclear charge of the lithium atom is +1 because it's being shielded by those two core electrons. And so generally speaking, then for the main group elements, as you move down, you get larger atomic radii going down. Because so if you look at lithium, it's +1, but then you blow to sodium, it's +1 as well, but now you've got that big amount of electrons there. So you have those so sodium has 11 electrons, and 10 of those are core. So that extra electron on the outside, it's really blown out further. So then it just gets bigger. And then as you move right across the table, the periodic table, the effective nuclear charge increases, and since the nucleus draws in the electron density, it'll shrink the atom size. So which electrons experience the greatest effective nuclear charge? So magnesium is in column 2, aluminum is in column 3, and sulfur is in column 6. So it's going to be +6 for sulfur. So transatomic radius. So for the transition metals, they're about the same size, and also with the valence shell, it doesn't change that much. So it's the effective nuclear charge is approximately the same because so remember so let's look at row number 4. You have 2 electrons in the 4s, and then the electrons go into 3d. But remember, 3d is 1 less in the principal quantum number than that, and so the 3d electrons that they're adding into the core versus adding into the valence, and because of that, they effectively shield the outside, and the effective nuclear charge does not change really for the atoms going across in the transition metals. So in cations lose electrons, and as they do, they tend to lose electrons towards a noble gas configuration. So aluminum, as it loses electrons, and it's going to lose 3 electrons, you take the 3 electrons from the highest number n first. So you don't take the 2 electrons from the 1s and 1 from the 2s. No, you take them from the highest n on the outermost shell. And so for anions, monatomic anions, likewise, when you add electrons, you add it in the valence, the outside electrons, and you add it to go towards a noble gas. So sulfur is going to want to grab 2 electrons. It's going to grab 2 electrons and be more like neon. Well, it's going to be the same configuration as neon, but sulfur in the -2 anion state. And so the cations, when metals loses the valence electrons, it has a lower energy valence shell, just like the noble gases. However, losing electrons is endothermic. It takes energy to rip electrons off. But why does it happen then if it takes energy? Well, then from the bonding. So if magnesium plus 2 ion is able to bond with a negative anion. So ripping electrons off, this is always exothermic. I'm sorry, endothermic. It takes energy to do it. So you have to rip the electron off of the atom. And when the transition metals form cations, when the transition metals form ions, the electrons are ripped off the highest n. So in the 4s is higher in the principal quantum number than the 3d. Therefore, when ions are formed, the electrons are removed from the highest orbital first. So that means the 4s electron for the transition metals in period number 4 for the transition metals. And something called paramagnetism and diamagnetism. So if something is paramagnetic, this means that there is one or more unpaired electron. So one or more unpaired electron makes something paramagnetic. And silver here, for instance, has one electron in the 5s orbital unpaired. And then if you look at zinc, on the other hand, zinc does not, all the electrons are paired, all spin up and spin down. And that means that silver will be attracted by a magnetic field, but zinc, on the other hand, will not. It will be slightly repelled by a magnetic field. So that's the difference between paramagnetic and diamagnetic as the magnetic properties of the atoms. We're not going to talk about ferromagnetism, so you can talk about that in future classes. So, and ionic radius. So ions in the same group, they have the same size, and going down the column, they increase in size as well. So like looking at the alkali ions, lithium, sodium, potassium, rubidium, cesium, they go as you go down the column, the ions get bigger. And also, so if you look at this, so cations are smaller than anions. So look at, so if you look across the periodic table, you have oxygen -2, fluorine -1, but then you go to neon, and then after that is sodium, and then magnesium. So sodium +1, magnesium +2. So fluoride, oxide, neon, sodium +1, magnesium +2. These are all isoelectronic. They have the same number of electrons. The difference is they all have 10 electrons, but oxygen has 8 protons, fluorine has 9 protons, neon has 10, sodium has 11, and magnesium has 12. So for isoelectronic ions, the fewer number of protons means a bigger ion, and then the highest number of protons has the smallest ion. So that's what we mean by isoelectronic. And but the general rule is that the positive ions are smaller than the anions, and with the exception rubidium and cesium, they're about the same size as fluoride and oxide, but rubidium and cesium are at the bottom of the periodic table, and rubidium and cesium tend to be they're not very dense. So that's pretty far down there. And I already mentioned about isoelectronic structures. So illustrating this, you can see down the periodic table that both the atom size and the ion size increase as you go down the periodic table for each element. And also they get smaller from left to right. Same trend with the ions. And so for these trends in cationic radius, same thing, same with the shielding. Same idea, the shielding. These electrons, they have the effective nuclear charge, but they're just bigger, and there's more stuff between them. So as you move down the column, it gets bigger. And also, why are cations smaller than the atoms? Well, you rip that electron off, and then the electron cloud shrinks. So generally speaking, when you rip off electrons, the electron cloud shrinks, and then when you add electrons, the electron cloud blows up. And that's because electrons are what give the structure to atoms, and they're negatively charged. So if you add negative charge to electronic cloud, it gets bigger, and if you remove negative charge, it gets smaller. So it's probably not too surprising to see that, because the electrons, they repel each other. And the same idea, just what I've just explained, using the electrons in the electron cloud. So just think of it as the electron cloud, and what's going to happen in the electron cloud as you add electrons. And so then the same periodic trends also for it goes on. In the isoelectronic, as I mentioned before, that means the same electronic structure. And for the trends, the smallest isoelectronic ion is the one that has the most number of protons in the nucleus, and the biggest one is the isoelectronic ion that has the least number of protons in the nucleus. So some trends here, so you can see moving down for anions, they follow the same pattern, going down a group. And the same explanations. You have the shells, and the shells are shielded by the inner electrons. So these electrons are further away from the nucleus. They have a weaker electronic. They have the same charge, but they're further away. So that means the Coulombic force between them is not as strong, and so the electrons are more loosely sitting on these areas. So, as I said there, same idea with isoelectronic anions. Adding electron density to anything just blows it up, makes it bigger. Ionization energy. So this is the amount of energy it takes to rip an electron off of an atom or ion. And it's always endothermic. It takes energy to do that. And we'll talk about the ionization energy. The first ionization energy, the energy to remove one electron. Second ionization energy is the energy to remove a second electron from the ion. And the third ionization energy is going to be to move a third electron from it, and so on. So the general trends in first ionization energy, they're opposite of the size. So basically, the bigger the atom, the easier it is to rip off an electron. So also the bigger the atom and the lowest effective nuclear charge. So the alkalis have very low first ionization energies, and moving to the right, the noble gases have high first ionization energies. So it increases moving to the right, and it also decreases going down. So because the atoms going down get bigger, the outermost electron has less attraction to the nucleus, therefore it takes less energy to rip it off. So that makes sense. So it moves across, and then you can see there's then the transition elements there. But you can see there is a bit of there's some irregularities coming here and there with this. But the general trend is that moving to the right, the ionization energy goes up, and then moving down a group, the ionization energy goes down. And that's also shown with this picture here of the same trend here. And there's a couple exceptions. You can notice that nitrogen and oxygen, you'd expect using this trend, nitrogen would be higher than oxygen. The reason is it takes more energy to rip off the electron, because nitrogen has all parallel spins, but oxygen has one electron that's spin down. So it turns out it's easier. Remember, chemistry is observational science. I'm not the one making the rules. This is what we're observing, and that's the reason why. And you can see there's the same trend for phosphorus and sulfur. But then you get to antimony, Sb, and tellurium. It returns. So that's weird. We had a trend, and then it switches on us. So what fun would this be unless there was exceptions to a rule, but then there's an exception to the exception, right? So that's the fun stuff you get in chemistry. is the rules within rules within rules that happens. So, and I mentioned this. It really has to do with the size. That the that the that the electrons are the further away they are, and also with the less charge of the nucleus, it's easier to rip them off. So, whereas a small atom with a very large charge, it's going to be hard to rip those electrons off of that. So, and that's what I've said. So, and there's exceptions. I mentioned this exception here that between oxygen and nitrogen because of the spin down in the 2p orbital. And it just takes a little more energy to rip that one off. And what about successive ionization energies? Well, if you look at sodium, magnesium, it takes a little bit of energy to rip off one electron, and then there's just huge jump in ionization energy. You go from close to 500 to 4,500 kilojoules per mole. It's a huge jump. Look at magnesium. You have the first ionization energy is relatively low. Second one's a little higher. The third one, it's a huge jump. That huge jump showing with that is gets to the noble gas configuration. So when you have an element and you're ripping off electrons, when you get to a very stable electronic configuration, there's going to be a huge jump in that, and that's the core electron. No longer the valence, that's the core electron. So that's one of the properties of a core electron versus a valence electron. And you can also see this chart here shows you that the higher ionization energy, you see the huge jump there. That's when we go away from the valence and into the core of the different elements. So basically what you just learned about ionization energies explain why valence electrons are more important than core electrons determining their activity in bonding of atoms. So they're the ones that interact. Since bonding involves transfer or sharing electrons, because they're held more tightly, or B, they're held more loosely, it's because they're held more loosely. So they're the ones that exchange. So the valence are the ones that matter. So chemistry is very superficial. We care about the valence most of all. We care about the core as long as they're good in the core, but nope, valence is the most important. The amount of energy that an element releases is something called electron affinity. So adding electrons to atoms, oftentimes, well, it releases energy, and that is known as electron affinity. So, and it's oftentimes exothermic, but it can also be endothermic. So, why is that? Well, it's why is it endothermic? Because adding negative electron density to an electronic cloud, it's going to blow up the cloud, and it actually might need energy to blow up that cloud. And don't forget that with the noble gases, especially, they're already pretty stable, so they don't really want to bond anymore. They don't want more electrons. So, and also, the greater the magnitude, the greater the electron affinity. And this is not a smooth trend, but it doesn't always work. So this partially tells us about the periodic table. You can't predict everything using periodic law, and there are exceptions, and then there are some things that are hard to predict as well. So this electron affinity does change. It's not a very smooth trend. So whereas size is a relatively smooth trend. I mean, there's even exceptions there, and ionization energy is a very smooth trend. But electron affinity is not a smooth trend, and there are some things. So generally becomes more negative from left to right. That makes sense though, because the effective nuclear charge is increasing. Look, it's not absolute. So and group 5A tends to be slightly lower because the electrons have to pair up, and groups 2A and 8A generally have very low because then the electrons have to go into a higher sublevel, and but the highest electron affinity are the halogens. They're dying to get electrons. So you can see here the trend tends to increase going from left to right, but it, I mean, doesn't always, because then you have the certain things like nitrogen here, for instance. It doesn't follow that trend, and so yeah, it's kind of interesting. I mean, there is kind of a general idea, but there's a bit of a pattern, but not too much of a pattern. And next, we'll talk about the metallic character of elements. And some things about metals. They tend to be bendy, so malleable, ductile. They're shiny, they reflect light, they conduct heat well and electricity well. They form most oxides are basic, meaning the opposite of acidic, and they tend to form cations and tend to be oxidized. Nonmetals, though, they tend to be brittle, and you can break them. They tend to be dull and non-reflective, and man, I feel sad for the nonmetals now. I think they're interesting, but according to textbook, they're dull. They tend not to conduct electricity or heat very well. Of course, there's exceptions to this. Carbon, graphite is a conductor, and diamonds are one of the best thermal conductors there is. Oxides tend to be acidic, and they can form anions, polyatomic ions, and they tend to get reduced more than oxidized, but they can also get oxidized. So, I mean, they're almost like opposite each other. It's like the nonmetals are the antimetals, almost. Metallic character, it's where the element's properties tends to be more like a metal. So more malleable, ductile, better conductors, and easier to ionize. And generally speaking, as you move to the right across a period, the metallic character tends to decrease. So further you move to the right, the less metal-like an element is, and going down a column, the more metal-like an atom becomes. So, if you look here, so metallic character decreases going to the right, and the metallic character increases going down, which also mentions hydrogen. You can see hydrogen. Where do we put hydrogen? Hydrogen is kind of in a category on its own, but we believe we haven't observed it yet. We've seen some evidence for it in some of the planets, but there might be a form of metallic hydrogen, where you have metallic bonding, where you have an array of nucleus and a sea of electrons, as what a metallic bond is like. So we're not so sure about hydrogen. I don't like this trend as much, but I mean, it does illustrate certain things. I mean, of all the nonmetals, carbon is kind of more metallic because carbon can conduct electricity and can conduct heat really well. But versus, say, fluorine, in the same period, it certainly does not conduct electricity. Also moving down columns, right? So you look at nitrogen. So nitrogen is definitely a nonmetal. Then phosphorus is definitely a nonmetal. Then you have arsenic and antimony, and these are kind of like metals. They're a little shiny. I mean, they get like they're kind of a luster to them. But then you get bismuth. The arsenic and antimony are not very ductile, though. They're kind of hard. But bismuth is definitely a metal. It conducts. It's shiny. You can bend it. So that is certainly a much more metallic character. So that's kind of the general trend. It's not a super smooth trend. But besides, like, does that mean that francium, element number 87, is the best metal? Is the most metalist of the metals? Not necessarily. I mean, the element alone that conducts electricity the best is silver. So just in the elemental form, does that mean silver is a super metal then? I mean, it's hard to say. I mean, but these trends are hard to compare within the metals, but within general ideas, you can see that they kind of do follow this. So, and generally speaking, metals tend to have smaller first ionization energies. So, but except for noble gases, maybe if we keep on discovering more elements, maybe the noble gas, um, uh, whatever noble gas elements or that are metals. Who knows if they even exist? We're not entirely sure. So, and the idea from this comes from quantum mechanics. So, they tend to be larger sized, and it's easy and further down the periodic table. So they tend to be the left and to be down, and then it's easier to rip off the electrons. But that's what the trend in the first ionization energy. Okay, so which statement best explains why sodium commonly forms a +1 ion and not a +2 ion? So sodium is only 1 electron. Sodium has 11 electrons, so that's wrong. All metals form +1 ion, and sodium is a metal. Well, not all metals form +1 ions. Sodium has only 1 valence electron, and that's easily removed. And removing a second electron would be more difficult because it's a core electron. There we go. We have our winner. Answer C. So let's talk about some of the metals themselves. So alkali metals. So radius increases going down. We've already talked about this. Ionization energy decreases. This is the opposite of the atomic radius. Also makes sense. Very low ionization energies relative to other things. These make good reducing agents because it's easy to get their electrons off. These are very reactive. So it's easy to get them to react. We don't find them in their pure form in nature. And react with nonmetals to form salts. This they do. And generally speaking, the alkalis are very soluble. Electron affinity decreases. The melting point also decreases going down the column, and it's very low for metals. So the melting point tends to be very low, and the reason is the bonding between a low melting point means that it's not a very strongly bonded metal. And density tends to increase going down the column, except for potassium. Potassium is the exception to the rule there. As you go from sodium to potassium, it actually decreases. So here is the general properties. So atomic radii, moving down a column, increases, and moving across the row, moving to the right, decreases. And the idea for that is moving down a column, the size of the electronic cloud increases, and moving to the right, the decreases because the effective nuclear charge increases. First ionization energy is the exact opposite of the atomic radii, and the reason for that is that it's harder to rip off electrons when the atoms are smaller and or have stronger effective nuclear charges. So electron affinity, there's not really any trend to this. Moving across the row, they tend to be more negative because the effective nuclear charge increases, and not a smooth trend, and it peaks around the halogens. Metallic character tends to increase going down a column, and it also decreases moving from left to right. And again, this is a fuzzy trend. And thank you for listening. Please join me for future lessons.